Okay, so we're studying heat and thermal energy. I have got two pots here, both containing water. There's lots of water in this one. It's at 50 degrees Celsius. There's a lot less water, less volume of water in this one, but it's at 80 degrees Celsius. Which has more heat energy? This one or this one? It's this one. No, it's not. The one's a higher temperature. The one with more heat energy is this one. Now, if we poured them together, which way does the heat energy flow? This one has more heat energy, this has less. Pour them together without burning anything. Which way does the heat flow? The heat actually flows. Why did I put them down? The heat flows from the object with a higher temperature into the object at a lower temperature, even though this one had more heat energy to start with. Are you confused? I hope not. If poured together, which way would the heat flow? The heat would flow that way. And when would the heat stop flowing? Well, the heat would stop flowing. Well, the heat would flow until the whole mass of water has the same temperature, in which case it would have reached thermal equilibrium. Thermal equilibrium is when everything is the same temperature. That's the definition of thermal equilibrium. Okay, now this brings us to a couple of key points that we need to talk about. One of them is internal energy. The other one is heat. What is internal energy? Well, all objects, all physical objects are made up of atoms, and these atoms are vibrating, which means if they're vibrating they have kinetic energy because of their vibration. And particularly solids, they have a reasonable amount of kinetic energy. The particles inside are vibrating, but because they're linked in position, they're held by molecular bonds, they also possess potential energy stored in those bonds. So solids have kinetic energy plus potential energy. In fact, internal energy is just the sum of the kinetic energy plus the potential energy of particles. Gases have a lot of kinetic energy and next to no potential energy. Solids have 50-50 and roughly the same amount of each. So that's internal energy. Internal energy is the kinetic energy plus the potential energy of particles. Now, quick note on this. Important to realize that the kinetic energy that we're talking about is the vibration of particles in their positions. If you drop a lump of wood from a plane and it goes plummeting down towards the earth, now the lump of wood has kinetic energy, and has lots of kinetic energy, and if it's landing near you, get out of the way, because it'll have so much kinetic energy it'll do something or someone a whole lot of damage. But that kinetic energy is not the same as the kinetic energy in the internal energy of a substance, because the kinetic energy we're talking about here is the kinetic energy of particles vibrating in their fixed positions. Very different. It's the random kinetic energy. Now, let's talk about heat. I asked you to start with which has more heat energy, this guy or this guy. And really it's not a very good question, because at this level heat is actually not defined as the amount of thermal energy something has, but heat is defined as the flow of energy from an object of higher temperature to an object of lower temperature. That's what heat is. So the definition of heat is the energy transferred from a body at higher temperature to a body at lower temperature. And this can happen through conduction, it can happen through convection, or it can happen through that other one, radiation. Heat can flow through any of those three means. But that is the flow of heat. Heat is a flow. It's not the energy, heat energy possessed by a body. It's the flow of thermal energy from one to another. Alright, that brings us to the final point. We talk about temperature. What is temperature exactly? Well, we no longer say temperature is how hot something is. That is just wrong, false, bad, wrong. Never say that in a test. Temperature is the average kinetic energy possessed by a body. It's the average kinetic energy possessed by the particles that make up a body. That random kinetic energy of the particles that are vibrating. The more they are moving randomly, the higher the kinetic energy, the higher the temperature. That's why as something gets higher and higher in temperature, the particles are moving more and more and more rapidly, till you get a gas, and in a gas the particles are moving with rapid random motion. Okay, how do we measure temperature? We've got two scales. We've got the Kelvin scale, we've got the Celsius scale. So the Celsius scale is the one we know, it's the one we're used to. It all begins, well actually, Celsius scale, there are the two fixed points that we know about. There's 0 degrees Celsius, where 0 degrees Celsius, where water changes from freezing to liquid phase, and then there's 100 degrees Celsius, where water will change phase or change state from liquid to gas or boil. And those are the two fixed points that we are very familiar with. But if you go down lower and lower and lower in temperature, you get to a point where it's as cold as it can ever get, much colder than anything you experience in your day-to-day life, and it's minus 273.15 degrees Celsius. At that temperature, everything stops, including atoms. There is no energy for anything. No work can be done. Now, that seems like a pretty arbitrary number, 273.15, but 0 degrees and 100 degrees make sense to us in the way we live, because they relate to things we understand. The freezing point of water and the boiling point of water. So another scale is the Kelvin scale. Now this makes less sense compared to our day-to-day lives, but it makes more sense when you think about what temperature actually is. Temperature is the average kinetic energy of the particles in a body. So at 0 Kelvin, the particles have 0 kinetic energy. That is absolute zero. That is where nothing can happen. We come up to 0 degrees Celsius, which is 273.15 Kelvin. That's equivalent. 273. See, 0 degrees Celsius is actually quite a high temperature. There's a lot of energy. 100 degrees higher, you've got 373.15 Kelvin. That's equivalent to 100 degrees Celsius. So these are related because 1 degree Celsius equals 1 degree Kelvin, but they start in different positions. In fact, temperature in Kelvin equals temperature in Celsius plus 273.15. There we go. There is an introduction to thermal physics.